Hello students, welcome to yet another lecture of Design and Analysis of Algorithms. The topic for today's lecture is P and NP problems. In this lecture, we will be concerned with the distinction between the problems that can be solved in polynomial time and problems that cannot be solved in polynomial time. So first let's define the class of P problems. Informally, we can say that P is the set of problems that are relatively easy. Then NP. NP is the set of problems that are very hard to solve. So P is the set of problems that can be solved by a deterministic machine in polynomial time. There are two things to understand here. One is deterministic machine. We will be defining this term after we introduce NP problems. But polynomial time. Polynomial time means any mathematical expression that involves n or n square or n cube raised to s. In general, we can say any mathematical expression that involves n in the form of this, n to some power constant c. C can be any constant, it can be 1, 2, 3 up to this. So any mathematical expression that involves any of these terms means polynomial time. Now let's define NP. NP necessarily means that it includes the set of decision problems that are solvable in, again, polynomial time but by a non-deterministic machine. So NP again involves two important terms. One is polynomial time and another is non-deterministic machine. So these are the set of decision problems which can be solved in polynomial time, but the difference between P and NP is that these problems, NP problems, can be solved in polynomial time by a non-deterministic machine. Now let's try and give a simple difference between a deterministic machine and a non-deterministic machine. The notion of algorithms that you may have encountered so far involves the operations which are well defined. Every operation is well defined. This means an algorithm with the property that the outcome of every operation is well defined, or we may say uniquely defined. This is a deterministic algorithm. So the outcome of every operation in the algorithm is uniquely defined. We know what the outcome of this operation is going to be. So till now you are concerned, or you are dealing with the algorithms, you may have dealt with the algorithms that are essentially deterministic in nature. Now, what is non-deterministic? It says that the operation, or we may rather say the outcome of operations is not uniquely defined, but is limited to a specified set of possibilities. So, any algorithm where the operations of the algorithm or the outcome of the operations of the algorithm is not uniquely defined, that is non-deterministic algorithm. You can never know for sure what the outcome of a specific operation of the algorithm is going to be. Rather, we have a set of possibilities that makes up the domain for the outcome of that operation, and such an algorithm is known as a non-deterministic algorithm. And any machine that works with non-deterministic algorithms is known as a non-deterministic machine. That was a distinction between the deterministic algorithms and non-deterministic algorithms. Now let's go back to NP problems. We said that NP is the class of or the set of decision problems that are solvable in polynomial time on a non-deterministic machine. NP doesn't mean non-polynomial time. You should understand this. NP means non-deterministic polynomial time. But how do we solve these problems? We solve them on a non-deterministic machine using a polynomial time and using a Lucke algorithm. What is a Lucke algorithm? A Lucke algorithm is any algorithm that makes a guess. It makes a guess, and magically enough, this guess will always be the right guess. That's why we call it as it's known as the Lucke algorithm, because every time it makes a guess, that guess will be right, and that's what we use to solve the NP class of problems. For example, if I have to solve 3 satisfiability problem, how can we solve that problem using a Lucke algorithm? Let us see. Let's first define satisfiability. Let x1, x2 be Boolean variables. Let xi dash designate negation of xi. A literal can either be a Boolean variable or its negation. So a propositional formula can be constructed using literals and the operations and or. For example, you can write x1, x2, x3, x4, or we can write x1 dash, x2 dash, this is negation, okay, and x3 dash x4. These are the formulas of propositional calculus. Now, satisfiability asks us to check whether this formula comes up to be true for any assignment of the values of xi's. The values of xi's, when we assign the values of xi's with the truth values that could be true or false, we have to check whether there is any assignment, any combination of assignment of xi's that gives the outcome of the formula as true. That's our satisfiability problem. So we have to assign values, true values for these xi's and check whether there is any combination of assignment that makes the whole formula as true. So like we can assign this as true, this as false, this as false, this as true, and then we can see whether this comes up as true or false. But the 3 satisfiability problem involves 3 literals. In each class there are exactly 3 literals. Now 3 satisfiability or 3 sat, it says given a Boolean expression of the form the important point to understand and remember here is that in 3 sat a class will always contain 3 literals, not more than 3 literals, exactly 3 literals. So let me define these again. These are our literals. This is the symbol for AND operation. This is the symbol for OR operation, or we also call this as a conjunction, and this as disjunction. This represents the negation of literals. So 3 sat problem asks us, can you set the values of xi's such that the value of formula comes out to be true. Can you set the values of these literals such that the value of whole formula comes up to be true? So this problem is NP. How can we solve this problem now? Now let's see how a lucky algorithm will solve this problem. What a lucky algorithm does is, it makes guesses. It makes guesses for every value of each literal in the formula. It makes a guess. Guess the value of x1. It can either be true or false. It makes a guess. Now it makes another guess for x2. It can be true or. In the same way, it makes guesses for all the literals in the formula. And magically, if there is a combination of the values that gives the true value to the formula, the answer will always be true. The answer will always be true. That's why we say it's a lucky algorithm. We are lucky enough to get the guesses according to our outcome. What we want the outcome to be, the guesses will, if there is a true answer for this formula, the guesses will always be according to that. The guesses will be the right guesses to get the true value for the formula. We have to understand one thing though about the lucky algorithm is that it's biased towards yes. What this means is that it will always provide the answer yes if there is a yes answer. If three satisfiability, if there is any combination of values that comes up as true, it will give us the guesses, the appropriate guesses. But if there is no such guess, then the lucky algorithm is of no use. It doesn't say anything about that. That's why we say that it's biased to yes answers. Let's define NP more formally now. So NP is the set of decision problems with polynomial size certificates and polynomial time verifier for yes. So NP is the set of decision problems with polynomial size certificates, and by certificates I mean the outcome of guesses. The outcome of guesses. These outcomes have to be of polynomial size. They cannot be of exponential size. And we also have a polynomial time verifier for yes outputs. What does that mean? That means any problem that can be, whose solution can be verified in polynomial time. For example, if again I have the 3 sat problem and somebody says that I have solved this problem, and he gives me the guesses for x1, x2, dash 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 up to maybe x8. He gives me the values for x1, x2, dash 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 up to x8. Maybe he says that x1 should be true, x2 should be false, dash 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 and x8 should be false. What I can do here is that I can put these values in the expression, the 3 sat expression, and I can see whether these values give me the truth value for the whole expression or not. So I can verify this solution in polynomial time. There's a polynomial time verifier for this solution. But this will always be for only yes inputs. It cannot be for no inputs. What does that mean? That means some guy says that if I have a chessboard and somebody says that this configuration is the configuration where white wins. A configuration where white has won. Somebody gives me a configuration saying that white has won. What I can do easily is that I can check that configuration in polynomial time whether white actually wins or not. But what if somebody says that white never wins? White never wins. I can never check this configuration. Somebody gives me a configuration and says that this is the configuration where white never wins. I can never check it because it's the same as solving the problem. So this polynomial time verifier for yes inputs is very important. We can only check whether your solution is the true solution if it says that yes, there is a solution. If it says no, there is no solution, we cannot check that. So all in all, NP is the set of problems with polynomial size certificates and a polynomial time verifier for yes inputs. So if we look at the relationship between P and NP. From the definitions of P and NP, it's quite evident that P problems can also are also solvable on NP. That means a problem that is solvable in polynomial time on a deterministic machine can also be solved in polynomial time on a non-deterministic machine. So P problems can be solved on a non-deterministic machine in polynomial time. This says that this statement says that P is the subset of NP, and that's the relationship between P and NP. Using the Venn diagram, we can show it like this. If this is our NP, then this will be our P. So P is a subset of NP. The more important question is that whether P is equal to NP or whether P is not equal to NP. This definition, this Venn diagram assumes that P is not equal to NP. That means there are some problems in NP set that cannot be solved in polynomial time. If P is equal to NP, that means that we don't know yet the efficient solutions that these problems may have. Not yet. We have not discovered those solutions or efficient solutions that these problems might have if P is equal to NP. But if P is not equal to NP, then this relationship says that P is a totally different set than NP. This is the relationship between P and NP problems. Now let's define reducibility. If we have two problems, L1 and L2, we say that problem L1 reduces to problem L2, also written as L1 reduces to L2, like this. If and only if there is a way to solve L1 L1 by a deterministic polynomial time algorithm using a deterministic algorithm that solves L2 in polynomial time. So what's reducibility? If we have two problems, L1 and L2, and we say that problem L1 reduces to problem L2, if and only if there is a way to solve L1 by a deterministic polynomial time algorithm using a deterministic algorithm that solves L2 in polynomial time. What does this actually mean? This means that a problem L1 reduces to problem L2. That means we are actually converting the inputs of L1 to the equivalent inputs of L2, but we are doing this conversion in polynomial time. This is very important. And by equivalent inputs, I mean that they have the same yes/no inputs. They have the same yes/no inputs. So a problem L1 reduces to problem L2 means that we are converting the inputs of L1 into the equivalent inputs of L2 in polynomial time. So what does this mean? What does this actually mean? What are we trying to achieve by converting a problem from one type of problem to another type of problem? Or rather we say what are we trying to achieve by reducing a problem to another problem? What we are trying to achieve is that this statement specifically means that L2 is as hard as L1. This statement gives us an insight about the difficulty or complexity level of L2 problem. If this is the case, if we could convert a problem L1 into L2, if we could reduce the problem L1 into L2, it says that L2 is as hard as L1. Or we can say that if L2 belongs to polynomial type, then L1 belongs to P. Or if L2 belongs to non-deterministic polynomial time set, then L1 belongs to NP. And in general, we say that L2 is as hard as L1. This was all about reducibility. Let us define NP hard now. A problem X is NP hard if for every problem Y that belongs to NP reduces to X. This is the definition of NP hard, and NP complete says a problem is NP complete if, or we may write it as a problem X is NP complete if X belongs to NP and X belongs to NP hard. So a problem is NP hard if for every problem y that belongs to NP reduces to X. We have to understand here that X cannot belong to P unless P is equal to NP. This is very important here. Okay. So and a problem is NP complete if X belongs to NP and X belongs to NP hard. Let's try and give the relationship among all four sets of problems: P, NP, NP hard, and NP complete. So let's give the relationship among P, NP, NP hard, and NP complete. We know from the relationship among P and NP, we know that P is the subset of NP. So if this is my NP, then this will be my P. And if this is my NP hard, this will be my NP complete set. This is the relationship among all four types of problem sets. So P is the subset of NP, and there are some problems which are in NP and both in NP hard. They are known as the NP complete problems. So this overlapping area, you can see it from the definition of NP complete that a problem is NP complete if it is in both NP and in NP hard. So this overlapping area is the NP complete, and that there are some problems which are not NP complete but NP hard. This is the relationship among P, NP, NP hard, and NP complete. Now, how do we prove if a problem is NP complete or not? How to prove? If a problem is NP complete or NP complete. Let's just leave it to that. So we can do it in two steps. First, we have to prove that the problem belongs to, if we call a problem X, we have to prove that X belongs to NP. And as you know, a problem is NP if it has a polynomial size certificates, if it has polynomial size certificates, and if it has a polynomial time verifier. Verifier but for yes. All right. So first we have to prove that X belongs to NP. We'll come up with an algorithm that has a polynomial size certificates and that has polynomial time verifier for yes. And second, we reduce from some known NP complete problem to problem X. and when we reduce from some known NP complete problem to problem X, we know that X is as hard as the known NP complete problem. That makes up the proof of the problem that it is in the NP complete set. Now, there is a problem, the 3-set problem, that was long proved by Cook in 1973, I guess, 1973. He proved that this problem, 3 sets viability, it's NP complete. So our work here is done. We use this 3 sets viability problem and we reduce from 3 sets viability to problem X, and we prove that we could prove that any problem is NP complete. So that was it from today's lecture, and we basically our concern of this lecture was to distinguish between the class of problems that could be solved in polynomial time and the class of problem for which there is no polynomial time algorithms. We saw that in P and NP class of problems. We saw that the NP is the class of problems, decision problems that can be solved in polynomial time on a non-deterministic machine and can be verified, whose solutions could be verified in polynomial time. We also saw 3 sets viability, how that can be solved by using a Luckey algorithm. Then we saw that we saw what NP complete and NP hard problems are, and we saw how we can prove whether a problem is NP complete or not. That was it for today's lecture. Thank you.